Welcome back, and hopefully the last video on the reactions of alkenes made a little bit of sense and you've started to be able to put together how it is that things add across the double bond. We're going to look at that in a little bit more detail now in terms of what happens if we react lots of molecules together that all have a double bond. And this is how we make polymers. And by polymers, we mean really, really large molecules. Generally, all the plastics that we use are made up of some kind of polymer. Nylon and other things like that that you may have heard of are also known as polymers. In chemistry, when we talk about polymers, we are literally talking about very large molecules that can be made from individual small molecules all being joined together. If you like to put things together visually, the way we do this is if you take, say, a whole bunch of paper clips and start to chain them together, the single paper clip would represent a monomer, and then when we start to chain them together, we start to get a polymer. And my paper clips are pretty dodgy in the way I draw them, but that gives you an idea of the way that we link them together. So for every polymer, there is a monomer, which is the small molecule we make it from, and then as we put these together we get different properties. Okay, so some polymers burn, some melt, others char or turn all black and give off bad smoke when they tend to be used. We don't need to know these properties that much in IB, but it is worthwhile noting that the properties of the polymer are very different to the properties from the monomer of which it is made. So looking at making polymers, again, it's just this idea of taking all the same, so these individual monomers, and then binding them all together so that we form these very, very long chains. DNA is a polymer that you're familiar with. It's a polymer of bases, so guanine, cytosine, adenine, and thionine. These bases polymerize together using DNA polymerase, and we end up with very, very long macromolecules, which are polymers. So when we looked at addition reactions, we looked at things where we added things across a double bond of an alkene. Now what we're saying is if we take something with a double bond and put it into a container with lots more things with a double bond, we can actually add these monomers to each other across the double bond. Okay, so if this is our monomer ethene, what happens is each one of these double bonds is going to pop open. This one's going to hold hands with this one here, popping open. We're going to form a new bond. This one will pop open and it's going to form a new bond here. This one will pop open with this one here and we'll form a new bond here. When that happens, what we end up with is all these double bonds breaking and forming single bonds. So our polymer will have single bonds if we start off with a double bonded alkene as our monomer. And the process of joining all these together is what we call polymerization. We will only look at addition polymerization within the standard level course. Okay, so all the polymers we're looking at will be addition polymers. As you can imagine, drawing very, very long polymers is a bit of a pain, so we tend to leave the ends open. You'll notice that there's nothing connected to this line here. It's open, and this one here is open. I usually draw little squiggles across them to show that they're open. This doesn't mean there's nothing there. It's just meaning that the polymer is continuing in both directions, that it is open and it's forming bonds and continues on. Okay, the other way that we can show that is by taking the repeating unit of the polymer. If you have a look here, it's a C here. Every two we're repeating. We take out one of those repeats, write what it is, open the bonds on each end, surround it in brackets, and put N. And this N is what is telling us the number of repeats, and it could be 20, it could be 50, it could be 1,000. Okay, so polymers are very long, and this is how we show them when we're doing them, when we're being a bit lazy and need to show them in easier ways. So what happens is when our monomers with the double bonds join to each other, the double bond is converted into a single bond. Okay, the monomers join together, and then we end up with a giant molecule. So this is how we make polyethene, where we take ethene molecules in the presence of a catalyst, and then it will form this C2H4N, and this is our repeating unit of our polymer. Okay, which makes the bit on the left-hand side, this is our monomer. Okay, if I have N amounts of my monomer, I will have N repeats in my polymer. So as I said, we take large numbers of ethene molecules in the presence of a catalyst, and we will form the polyethene polymer. Polyethene is a hydrocarbon like all the other hydrocarbons that we've looked at. It has only carbon and hydrogen, so it's going to be non-polar, as would be any polymer that we make from a non-polar monomer. Okay, and we can see this in the way that plastics behave. They don't dissolve in water or anything like that. They have more in common with oils and fats than they do with polar compounds. So because it is nonpolar, it only has dispersion forces between chains, or London forces between chains. So they tend to have low melting points and boiling points. We can vary the atoms on ethene monomers and produce polymers with different properties, so we can kind of tune it depending on what we hang off the polymer. Okay, so we can hang maybe a benzene group off it, or we might hang a carboxylic acid off it, or something like that. And by hanging these different functional groups off our polymer chain, we can vary the properties that we see. And this is what we do when we can, say, perhaps take a alkene that has a chloro on it. Now that we have this electronegative element, of course, we're going to form a dipole at different points along the chain, and this will change the nature of the intermolecular bonding. Now when we look at having the chloroethene, the polychloroethene, it will be a little bit polar, so these chains are going to be attracted to each other a little bit more. So we would expect the boiling points and melting points to be higher because the intermolecular forces between the chains are higher. Remembering that whenever we're talking about melting points and boiling points, we really need to be concentrating on explaining what's going on with the intermolecular forces. So ethene is going to have weak van der Waals or dispersion forces only. Polychloroethene is going to have a stronger dipole-dipole interaction, so would it have a higher melting point and boiling point. This is PVC. As you can see, PVC is, we are very familiar with polyvinyl chloride, okay, and this is made from our chloroethene, okay, and it's used in a wide variety of uses, including electrical insulation. This is because it tends to put itself out. It doesn't catch fire. It's easily molded and has a nice glossy finish, so it tends to be used in a lot of different consumer products. So, as I said, the only type of polymerization we do is addition polymerization, which means that our monomer must contain a double bond. If a monomer doesn't have a double bond, we can't have addition polymerization. So it must have a double bond between carbon atoms. Okay, if it doesn't have that, then we don't have a monomer. We can change the functional groups that are hanging off the monomer, which changes the nature of our polymer, and then depending on what the intermolecular forces are doing, that will determine its melting point, boiling point. It can also affect its plasticity, its rigidity. There's a whole number of things that it can affect. Okay, the other thing to note is that the empirical formula of the polymer is the formula of the monomer. So in the case of polyethene, it was C2H4, and remembering that this was the repeating unit of our polymer. We will have practice drawing polymers from monomers in our next lesson. So that is now the last of the addition reactions that we need to do for alkenes. So we've talked about the fact that alkenes can undergo combustion reactions, that they can be hydrogenated to turn into the corresponding saturated alkane using a metal catalyst, that we can add a halogen across the double bond, forming a dihalogenoalkane if we're using Br2, Cl2 or I2. We can form a single substituted halogenoalkane if we use HCl or HBr or HF. We can form the alcohol by reacting with water, and it can be with concentrated sulfuric acid, but more commonly, and that should have a 3, more commonly it's the H3PO4, which is our solid phosphoric acid catalyst. And we've also talked about polymers, where we have to have a catalyst and the nature of the polymer will change. The nature will be determined by our monomer. Okay, this one here, as you hopefully would suspect, is a couple of economic importance points. So make a note of these. These often come up in exam questions as to why we're interested in polymers or why we're interested in the importance of alkenes in terms of economic impact and effect. Okay, so just make a note of where we use these in industrial situations. And that's it for the reactions of alkenes. Next up, the reactions of alcohols.